Today we are looking at index laws, so specifically how we can solve equations or simplify expressions involving exponentials. Now, being able to solve exponential equations is very likely to be on the exam. There is almost always on exam 1 a question involving either index laws or log laws that we're going to get to in the next session. So we're going to go through these today and do a few examples. Most of these index laws you'll already know from the past. You will have learnt about them in Year 8, Year 9, Year 10 and again when you did Unit 1 and 2 methods. So the first one, and I'm sorry if you can't see it clearly on the screen, you have it in front of you in the booklet as well. If we have the same base and we're multiplying, we add the powers. Now I'm going to go through and explain to you why these rules work, proving to you why they work. What you might like to do is to consider if you'd like to watch this. If you either already know where they come from, why they work, you might decide to fast forward until we get to the examples, and that's fine. Or if you really don't care about how they work and you just want to know how to use them, then you can also fast forward. But for those of you who are interested, this is where they come from. So if I'm multiplying a to the power of m times a to the power of n, this means that I'm going to have a times a times a times, and I'm going to write that m number of times, okay? I then have the multiplication sign that we had in the second, in the middle here, multiplied by a to the power of n, which means that I have a multiplied a multiplied a, and this keeps going for n number of times. If I'm thinking about that to work to then write this in index form, what I need to do is to think about how many a's have I multiplied together here. Well, I've got m a's written here and n number of a's written here together. That means that altogether I'm going to have m plus n. I'm going to have m plus n number of a's, which is where this first rule comes from. The second rule for division is very, very similar. Remember, all of these rules are related to having the same base. So I've got the same base here. When I'm dividing, I subtract the powers. So if I think about that, if I'm doing a division, it is the same as writing it as a fraction. The division sign is actually showing that I've got something in the numerator divided by the vinculum in the middle, something in the denominator. So that's what I have here. I can write this out as well. am to the power of n, I've got this there, m times, however many times that is. I've got them there m number of times. Over in the denominator, a times a, however many times. N number of times. What I do then is I start trying to cancel things out. So if I had, for example, let's stop and look at a specific example. If I had a to the power of 3 divided by a to the power of 2, what we would do is that we would cancel out. A divided by a is 1, a divided by a is 1, a and a cancel out. I would be left with 1 times 1 times a is a, over 1 times 1 is 1. I'm left with a, and when a power is not written, it's to the power of 1. And 3 minus 2 will also give us 1. So if we look back at our general example, our general case, I'm again cancelling. I'm going to keep cancelling all of our a's until at one point I have a certain number left in the numerator and none in the denominator. So I'm going to cancel out until I have none left in the denominator, hopefully. That will get rid of all of my n number. However many I have left, I would find, because it will be equal to a of m, however many I had here, I've cancelled out n many of them. So I have to subtract n. I'm subtracting the number that I've cancelled out, the number that were in the denominator. Our third log law, where we've got brackets, we multiply the power. And we can prove this one by using our first law that we had. So what this actually means is that I've got a to the power of m, I've got it there, this part is multiplied by itself n times. So I have this multiplied by n times. So if we're thinking about what's going on here, when we need to work out our new power, our rule is that we add our powers together when it's expanded like this. If I'm adding my powers, m plus m is 2n, plus m is 3n, plus m is 4n. If I've got them n times, I'm going to be adding them together. So for 3, if the power was 3, I would have 3m. If the power was 4, I would have 4m, so I have 4 lots of those when I'm adding the powers. The power is, if it's there n times, that means I would have nm, lots of them. So we're getting a to the power of mn. And again, you can prove it to yourself using a specific example if you would like. A squared to the power of 3. A squared is there 3 times. That's what we had from our power here. That's what this means to write it in expanded form. From our first index law, we know that when the bases are the same, we can add our powers. 2 plus 2 plus 2 gives me a power of 6, which matches to our 2 cubed that we had here. Our fourth index law, the 0 power. So what we're doing here is we're looking at 2 different things. If we're again doing this in a general case, let's think about if we took a to the power of m divided by a to the power of m. Our second rule tells us that when we're dividing with the same base, we subtract the powers. If I have anything minus itself, we get an answer of 0. If I then consider this in a different way, if I think about this, because remember division means the same as writing it as a fraction, if I think about writing this as a fraction, and remember I have the a's written here for m number of times, so that's going to go along m times and m times down here. When I'm cancelling, a goes into a once, a goes into a once, once, once. As I keep cancelling, because these values are the same, there will be the same number of a's in the numerator as there are in the denominator. That means that all of our a's will cancel out, and we will just be left with 1 times 1 times 1. We'll be left with 1 over 1, which equals 1. Because our 2 starting expressions were the same, that means that our 2 ending expressions are the same, and we get that anything to the power of 0 is always equal to 1. And this is a really important rule to keep in mind. Our final index rule that we need to know relates to negative powers. And again, we can consider this in a couple of different ways. So if I start off with a situation, and probably in this case it's easier to show it in a specific example. So let's say, let me make a smaller number actually. Let's say a cubed divided by a to the power of 5. If I use out the second index law, subtracting the powers, 3 minus 5 gives me negative 2. If I then look at our other way of looking at it, we write it as a fraction. We write it in expanded form, and I cancel like I was doing earlier. What I have left with is just 1 in the numerator. In the denominator, I have a times a, which is a squared. So we're showing that a to the power of negative 2 is equal to 1 over a squared. This is where, and we can generalise this, but it's a lot more difficult to show in general form, but what we're getting is that anything to a negative power is the same as 1 over that base to a positive hour. You need to be careful here when we're looking at this. It is not, if I had a negative in front of the a, that wouldn't change. This whole thing would still be negative. All that's changing is the sign of the power. So if I move a term from the numerator to the denominator, or from the denominator to the numerator, the sign of the power will change. Alright, so these are rules that you would have covered before. If you're just joining us again after fast forwarding, let's look at these examples together. Okay, so we need to simplify this. We need to think about which rules to use first. Once again, feel free to pause this and try it for yourself, or else we can have a look at it together. We would want to first off expand our brackets. when we expand the brackets, we're using our rule that says we multiply the powers. Remember that when anything is not written, there is a power of 1. So this is 2 to the power of 1 and x to the power of 1. So when I expand my brackets, I would have 2 to the power of 1 times 2 is 2, x to the power of 1 times 2 is 2, y to the power of 2 times 2 is 4. Then we can use our next index law. When we're multiplying, we add the powers. Now, we should work out what our numerical value actually becomes. So let's work out what this number will be. 2 to the power of 2 is the same as 4. So we've got 4 multiplied by 3. We multiply those numbers just like we would any normal numbers and we get an answer of 12. X is going to be to the power of, so we add the powers, 2 plus 2, it's a power of 4. Y, again, same base, when the base is the same, we add the powers, 3 plus 4 to give 7. So this is quite a basic question. This is a Year 9 level maths question, to be honest. You won't get asked anything this easy on the exam, but we'll start with this and we'll work up. So moving on to a more difficult question. Solving exponential equations, and this is something you're much more likely to see. One thing we need to remember with our exponentials, if our bases are the same, then if our bases are equal, then our powers will need to be equal as well. We have this here that's written as 3 to the power of x minus 1. You need to think, what can we write 27 as? 3 to the power of something. So, have a think, 3 to the power of what is going to give me 27? And it would be to the power of 3. No it wouldn't. Yes it would. 3 times 3 is 9. 9 times 3 gives me 27, which is what I wanted. Now because the bases are the same, that means that the powers must be the same. So we would get x equals 4, which is our final answer. Next question we're looking at. Now, this type of question comes up commonly every year. And this is something, well not every year, sorry, but quite often, every couple of years on the exam. This is something I want you to really think about what's going on. To identify this kind of question, it's when we're looking for different powers of x, when we've got a 2x and an x. That's what we're looking for, when we've got powers of 2x and x. Because this is suggesting I've got powers of 2, powers of 1, I've got the same base. What this is going to become is actually a quadratic expression. And you would have seen some of these last year. What we do is that we let a equal 5 to the power of x. So our 5 from here is the base, the power of x, because that's what's written there. You can't use let x equal because we've already got x's up there. It's something different. We need to choose another letter. Now we can substitute this in here. So I would get 5 from here, in between the brackets when it's not written as a times sign. Now if we think about this, 5 to the power of 2x. This term is the same as 5 to the power of x squared. Because we know the powers, if I put brackets, I multiply the powers. 2 times x will give me 2x. That was our third index law we covered before. If I'm substituting a in here where the 5 to the power of x was, I would get a squared. So I have 5a squared equals 26. Instead of this, we get a and minus 5. It's a quadratic expression. To solve quadratic expressions, we need to set them equal to 0 and use the null factor law. So I'm going to take everything to one side. Now we need to factorise. And remember, a lot of these questions are tech-free, so get used to doing them without a calculator. The only factors of 5a are going to be 5a and 5. The only factors of 5 are going to be 5 and 5. Because this is a positive here, we need to multiply to get a positive, but add to get a negative. Both brackets are going to need to have a negative. So we have negative 25 minus 1 will give me the negative 26. This tells us that a equals 1 on 5 or a equals 5. We now need to consider what x is equal to. So this is really important. These are our values of a. What does x equal though? So we substitute this back in. We were told 5x is equal to a. So instead of a, what we get is 5x equals 1/5 or 5 to to the power of x equals 5. This one here is quite easy. When it's missing a power would be 1, so therefore we get x equals 1. Over here we need to somehow, again, we want to equate the bases. We need to write 1 over 5 as 5 to the power of something. Using our last index law, we know that if we move the 5 to the numerator, the power will change from a positive to a negative value. Therefore, x equals negative 1. So our possible answers are that x can equal negative 1 or positive 1. We think, are these both possible? Well, yes, we know for exponential functions, that's what this is, 5 to the power of x. The domain is all real numbers, so we can have x as being negative or positive. We've got one last question to look at. So this is very similar, a very similar type of question, but it was on the exam. There is a slight difference. I would recommend that you pause and have a go yourself. If you're not confident, if you've got no idea, then feel free to keep watching. How do I recognise this? Well, we've got powers of x in more than one place again. But this time I don't have a 2x. And when I'm looking at the bases, they're not identical. I've got a base of 4 and a base of 2. So what I can do is to see though that 4 is the same as 2 squared. 4 is the same as 2 squared, and to the power of x. Minus 15 times 2 to the power of x equals 16. Now we can see, this is starting to look more like what we're talking about. 2 to the power of 2x, that's the same. We can expand the brackets, 2 to the power of 2x. We can rewrite it as 2x to the power of 2, because again, if I was multiplying, I would get 2x. I would get 2x, the power is not changing. And now this looks very similar to the question we did before. So if you got up to this step and you were unsure, here's another chance to pause and try the rest like we did for the previous question. But we will again let a equal 2 to the power of x. So I would get a squared minus 15a equals 16. Once again, I take everything to one side. Set the equation equal to 0. Once again, I need to factorise. We need a negative 15 when we add these together. So I get a value of a is negative 1 or a is positive 16. Once again, the question isn't asking me to find the value of a, it wants me to find the value of x. So I need to substitute into this. What is a? Our value of a was 2x. 2 to the power of x equals, that was negative 1 equals negative 1, or 2 to the power of x equals 16. Now let's think about this. I'm wanting to find when 2 to the power of x equals negative 1. That means I'm wanting to find when the y value of this function equals negative 1. If I consider this function 2 to the power of x, so y equals 2 to the power of x, if I'm sketching this like we did last time, we have an asymptote at x, my function will look like this. When I'm wanting to know where this function equals negative 1, that means I'm wanting to say, is there anywhere that y is equal to negative 1? Looking at our function here, there is nowhere that this function, that y will be equal to negative 1. That means we're looking along here. We're not going to get a point there. That means that this is an infeasible solution. And we need to give a reason why. You must show me that you see that there are 2 possible values of a, you see there are 2 possible solutions, and you're disregarding one. You can't just go straight to the other solution, you need to show me why you're disregarding it. So what we can say is that as 2 to the power of x must be greater than 0, which it has to be because all of the y values are greater than 0, this solution is infeasible. Okay, so we need to give a reason why. If we look at our option here, again we want to write with the same base, 2 to the power of, 2 times 2 is 4, times 2 is 8, times 2 is 16. We get the power of 4, so x equals 4. And so our final answer is just that x equals 4. don't forget, like I said before, we must do this part here. We must show why a solution is infeasible. It's not enough just to disregard it. It's not enough just to say it's not equal to. You need to give a reason why. Alright, that is it for today. So your task now is to make sure you've written everything down. If you have any questions, make sure you bring them into class next lesson. If you would like to get started on exercise 5C, you are most welcome to, but we will do some work on that in class. Okay, thank you very much and see you next time.